Remember we talked, as we're talking and thinking about the energetics involved with like high energy molecules and where they move and stuff like that. One of the concepts we've already discussed is heat of vaporization. Remember it was delta H VAP, heat of vaporization. And it had to do with the amount of energy that was necessary to vaporize 1 mole of a substance. In other words, turn it into gaseous form. Well, we can apply the same concept to, because we were talking about boiling point, we just now finished talking about melting point. We can apply the same sort of math to, instead of at the boiling point, we can apply it to the melting point. Okay? So instead of saying heat of vaporization, we can say heat of fusion. In other words, turning a liquid into a solid or vice versa, okay, at that point. So the amount of heat needed to melt 1 mole of a solid instead of vaporize it, okay, if we want to melt 1 mole of a solid and go from solid to liquid form, the amount of heat necessary is called the heat of fusion. Okay? Now, that's just an old word. You think of fusion as like fusing things together. Technically, that's not what's happening. That's just an old term that has been carried over through the years, and they just keep using it. Now, excuse me, we also know that we talked about freezing versus melting. They're the same point. They're sort of the same thing, except we're just going in opposite directions here, right? Melting is going from solid to liquid. Freezing is going from liquid to solid. But the point at which they convert over is the same temperature, the same point, what we call the melting point. Okay, so like I said before, it can also be considered the freezing point. So whenever we refer to something turning into, like usually we say freezing, but we're talking about a liquid turning into a solid. We also call that crystallization, okay, forming some sort of solid formation. So we've got heat of crystallization and the heat of fusion. Those are the same. They should be equal, but opposite, okay, in terms of their value. This is the amount of energy necessary to melt something. This is the amount of energy necessary to freeze something. So obviously, it should be the same, except one should be positive, one should be negative, and in terms of which way the energy is either going in or being drawn out of, that kind of thing. Okay. Now, when we think back to the heat of vaporization, notice this comment that I made here. The heat of vaporization is greater than the heat of fusion. And that's important to realize because when we deal with gases, gases are these collections of molecules that are extremely high energy, intense molecules. So if you're going to separate all of the particles away from each other and break those intermolecular forces, put them all the way out in gaseous form, that's going to take a tremendous amount of heat energy to make that happen. Just to make it separate from solid to liquid, realize you've not completely separated them out. You've just moved them farther out. That doesn't take as much energy, obviously, as it would to do a vaporization. So the heat of vaporization is always a lot bigger than the heat of fusion. Okay, so as far as the melting point of some of these substances, to go back at some of the ones we've already looked at, water, rubbing alcohol, acetone, ether, notice the melting point is where it would turn from solid to liquid. Water's at 0 degrees Celsius. We're familiar with this, but take a look at something like ether. Look how cold it would have to get for you to take liquid ether and turn it into a solid, okay, under normal atmospheric conditions. Not really an achievable temperature. That's why it's pretty hard to freeze. You can't just stick it in the freezer and freeze it. You put water in the freezer, it'll freeze, right? But if you put alcohol or anything with alcohol in it, some stuff like that, it doesn't freeze when you put things like that in the freezer. And the reason is because in the case of isopropyl alcohol, like rubbing alcohol, even though it looks like water, it won't, we'll talk about this later, but you also know that when you take water and put it in the freezer, it expands, right? So it can crack the stuff that you put it in. We'll talk about that in a little bit, but alcohol won't do that. Look how cold it would have to be, like negative 90 degrees Celsius to even get alcohol to freeze. So it's not an issue. Okay, sublimation. Sublimation is a process. So we've talked about evaporation. We've talked about condensation. Know what those are. We've talked about boiling. Know how that's different than evaporation. Sublimation, on the other hand, is when you take a solid like dry ice, like CO2, that has been cooled tremendously to the point where it's loosely held together in solid form, and then all of a sudden exposed to an environment like this, it actually goes straight from solid form, skips a conversion into a liquid because of the drastic energy difference, and it flows right into the gaseous state. So these molecules, because they're so loosely held together and require so little energy to separate them from each other, when they are exposed to our environment, the CO2, instead of just slowly spreading out and first becoming a liquid and then gaining more energy and becoming a gas, they actually immediately start separating from each other with enough energy to be straight in gaseous form. That's called sublimation. Okay. It's obviously endothermic. Okay. What happens with dry ice as it's subliming, it is absorbing energy from the surroundings. It's going into that system, into that piece right here. Because we're releasing high energy molecules when this happens. Okay, so we've been talking about these intermolecular forces. We know that we can overcome them, and if so, we get a gas. We can create more distance between them. That's how we get liquid, things like that. But what are they? Why are these molecules attracted to each other? Why, when we look at this picture of CO2, why are they like that? In really cold form, why do they even stay together? When we have water and we pour it out on the desk, why doesn't, as soon as it leaves this container, immediately disappear? Why does it stay together in that liquid like it does? What about those forces? What creates those forces? And that's what we're getting ready to talk about now. Okay, pretty much everything has to do with the attraction, what's called electrostatic forces. Attraction between positive and negative. We don't really know why. In chemistry or in life, we don't know why opposites attract. It just does. Okay? What we'll look at is, and what we're going to see is, whenever we have a positive region and we have a negative region, they tend to want to gravitate towards each other. They tend to want to move toward each other and be attracted to each other. And it's very important. I just said that, but it's very important that you understand that in chemistry and in physics, we don't understand why this happens. We cannot tell you what positive is and what negative is, other than the fact that we can just assign it and recognize it and note that they are attracted to each other. It's just like gravity. We see it every day. We know that it's real. No one questions it, but no one really knows what it is. We know that it's a force. We know that it's here. Everything that has mass has gravity. The more mass you have, the more gravity you have. However, to define what gravity is, you can't. Only thing you can say is it's a force that exists and is proportional to gravity. That's it. And it draws things towards the center. There's a center point. Wherever you can find the center of mass of something, that's where all the gravity is headed towards in all directions. But we really don't know what it is. So, anytime we have a positive-negative situation, we can have a force of attraction. Now, with ions, this is easy to think of. We've already talked about ions, cations, anions. Naturally, that makes sense. However, we're going to bring back now a little bit about what we did in the molecular modeling chapter. When we did molecular geometry and stuff, we talked about polarity. We talked about, are some molecules polar and some nonpolar? Now that becomes very important, because when we have a polar molecule, we have regions that are more positive and more negative, right? So that means there are little positive and negative areas, even though they aren't charges, they aren't cations and anions, they're areas that can be attracted to other areas of nearby molecules. And that's what's going to start creating these intermolecular forces. Okay? I'm going to mention this right here. Well, first, notice like the positive end of a polar molecule could be attracted to the negative end of a nearby polar molecule, right? And vice versa. Now, there's something here that says hydrogen bonding is especially strong. I'm going to skip that for a minute because I'm going to come back to it. Instead of trying to explain it now, I'm just going to devote a couple slides to it later on. So we'll come back to that. Now, the larger the charge difference, the stronger the attraction, right? If there's a bigger difference in the positivity and negativity of two things, the more they're going to want to be drawn towards each other. The smaller the difference in their charge, the less attraction there's going to be. Now, what's interesting though, because you may say, well, what about CO2? I'm just going to pretend like you would ask me this. Okay? If you consider CO2 is, think of the Lewis structure in your head and build the molecular model in your head. You'd have a carbon atom in the middle, right? And two oxygen atoms on either side. You'd have a double bond between the carbon and each oxygen. Okay, so you would have eight total around your carbon. You would be happy. You'd fill in, there'd be some dots around the oxygen you have to put in, right? So there's your Lewis structure. Is CO2 polar or nonpolar? You don't even need to know the electronegativity values to answer this. You just got to look at what you know about the geometry of CO2. What would be the geometry of CO2? Linear. If the geometry is linear, even if you had polar bonds between the C and the O, would the whole molecule be polar or nonpolar? Nonpolar. Why? Yep. Equal on opposite sides, right? They balance each other out. All right, so CO2 is a nonpolar molecule. So that if it's nonpolar, that means it doesn't have like a positive-negative end anywhere, right? But we just saw a picture of dry ice. We just saw how CO2 could orient itself in a situation to hold itself together, at least under really cold temperatures. So if they're not polar, how do they do that? Even nonpolar molecules will have very small, transient, meaning they don't last but fractions of a second, and then they're gone. They will have temporarily, I guess would be the right word there, induced dipoles. Now what does that mean? Dipoles, di means two, poles in reference to the polarity stuff we've been talking about. A dipole is a moment in time when polarity exists, and you have two poles. Okay? It's sort of like the same explanation as what polarity would be. Okay? So a dipole is a moment where you have identifiable opposite ends on an atom in terms of the electrostatic charge, positive area, negative area, okay? Partial positive, partial negative. Now, how is it then that a nonpolar molecule can exhibit anything like a temporary dipole? Well, let me show you. The way this happens is through a phenomenon that we call dispersion forces. Remember what disperse, to disperse something, what that would mean, to kind of spread it all out, right? So keep that definition in mind. Dispersion forces, they're also called London forces, also called London dispersion forces, also called van der Waals forces. The name doesn't matter as long as you understand what they are. Okay? Everything that exists, anything that is made of matter, and thus atoms, possesses dispersion forces. And the reason they possess dispersion forces is because of the electrons that float around. Okay? Every atom has floating electrons around it. And we now know enough about quantum mechanics to know that electrons are constantly appearing and disappearing and moving all around the outside of this atom, right? They don't just get in these fixed orbits and spin around. They're popping in and out, they're appearing, reappearing, and we have probability maps, the 1s2s, the 2p6s, of where they could be at any given time, right? We already learned about all that. Well, because there's so much movement with these electrons, what gets created by virtue of that are these dispersion forces, dispersing and movement of all those electrons around. Okay? What happens is one molecule or atom or whatever can come up to another one. And the fact that electrons are present in this one, and I bring up one next to it, and it has electrons present on the outside of it, what you can sort of get is like the example where, say I have two bar magnets. I put one here, and the north end is pointing this way, and I take this one and point the north end towards that north end. They don't attract, right? I can repel them, and I can push that, without ever touching it, push that magnet all the way across the table. Well, realize that has to do with electrical charge as well. If I take electrons and push them towards other electrons, guess what these electrons are going to want to do? Move away, right? Like charges repel each other. You can start seeing this shift. Like if this were the electrons around this atom, here's the electrons over here. If these get a little bit closer, you start seeing fluctuations according to the movements. Right? Instants in time, they start repelling each other. They shift them around. They sort of disperse them. If there's a lot of electron moving over this way, you get a big dispersion of the electrons over here. When you do that, you can create areas on this guy over here, create areas where there's more electrons now on one side than there would be on the other side, just by virtue of the fact that these things are moving around. Does that make sense? Do you see what I mean? I'll try to show you a picture here. Let's say this is a normal situation, and now these, I don't know why the picture I got has ovals on it, because spheres would be better, but whatever. Two atoms coming next to each other. What can actually happen? Maybe I just elongated instead of squashing down. I don't know. But notice what happens here. If there's you got to imagine all this happening at the same time. It's kind of mind-blowing, but If you have electrons next to this one, electrons next to this one, they start pushing each other in, you would think that maybe all the electrons then would go opposite ways, right? They would want to repel from each other as far as they could go. Well, what you got to realize is in so doing, whenever this happens, if this electrons over here sort of start to get pushed away, notice that what now is exposed is more of a positive charge, right? Because that's what the nucleus is. It's protons. So we know that opposites attract, right? So now that you've got some exposed positive charge, you're going to start drawing some more negative charge from this direction. So you get a lopsidedness over here. See that? These electrons over here could start hanging out a little bit more. It looks like there's a little bit more of an electron density on this side of this atom because of this attraction right here. Now, this is not a strong attraction. It's very weak. These things aren't going to lock up by any means. It's just enough to distort where the path of things are. That's it. And that means now that, because of these guys hanging out here, and it's situated itself where now you've got this temporary dipole in both of these atoms. You've got a little bit of an area right here where it's partially negative on this side, partially positive on this side. Partially negative on this side, partially positive on that side. Now, this is very weak. Like I said, this is not a chemical bond. This will not hold things together. But it can loosely keep things in a general position. Keep them from, for a moment in time anyways, from maybe completely separating apart from each other. Okay, just enough to hold them in. Because you've got to imagine this is happening in billions and trillions and just innumerable amounts of these atoms all floating around at the same time. Okay? Let's take a look. Look at a helium atom. Helium, it's easy because we only have 2 electrons, right? Now, let's consider another option here. We know that in the case of helium, the electron structure is 1s2. It has 2 electrons. There's my sphere. There's my 1s2 level. And we know also that in the case of helium, or in the case of any element, that the electrons can appear and disappear. We don't know where they are going to be any point in that sphere. They could be anywhere in that sphere. Okay. Now, let's say we took 3 freeze frames, just snap, snap, snap at any given moment in time, and we could stop and actually look. We know we can't do that, right? Heisenberg's uncertainty principle. We don't know. The fact that we are observing changes how an electron behaves, but let's just say we could. And we could freeze time, and we looked at this, and we looked and saw where these electrons were at any given time. In the first frame, we see that the electrons around the helium are here. The second frame, we see that now they're here. The third frame, they're over here. Notice that there's a difference in these in terms of lopsidedness of charge. Okay? Over here, things are sort of balanced out. It's hard to say. Over here, you can see it's pretty well balanced out on either side of this nucleus. However, over here, you start seeing an area where there's more electrons in one area than there is somewhere else. Actually, a focal point starts to occur, to the point where we could label that as a partial negative area, and by virtue, by default, over here there would be the partial positive area. Now, you can imagine that that would only exist for a momentary fraction in time, right? Because then we're back to something like this again, and we got all these fluctuations. So it's kind of hard to imagine. It's hard to say, why isn't that lopsided? That's sort of lopsided. There's, you could maybe say negative over here. Well, we don't have a fine line because we can't look at any of this. There is no point at which we can say, okay, now it's a little bit polar as opposed to not. We just have to assume that there are situations like this that can occur to where they get close enough together like this to where something like this starts to occur. Okay. Now, what you need to imagine is this is only 3, let's say this is 3 different helium atoms all at the same time. Okay. What you need to realize is when we have a sample of helium gas, we have who knows how many helium atoms all jumping around like this all at the same time. In that sample, there are going to be weak attractions between, very weak, but there are going to be weak attractions between all the helium atoms to one another in that sample. This is why the kinetic molecular theory, when we talked about gases, is not true. We said that everything was perfect, and there's nothing that would draw, there was no forces between the molecules. They were perfect. They would collide, they would bounce off, they would hit the walls like ping pong balls. Well, we know that that's not true because these forces do exist. And there are moments in time where a helium atom actually is weakly attracted to a nearby helium atom just because of the way their electrons are moving. Okay? So if you notice here, like if we could imagine this, if this scenario panned out, you could have 3 helium atoms that look like this at any given instant, And notice how they could orient themselves to be weakly attracted according to opposite charges. Okay? You can see the trouble with this in terms of being very weak. That's why helium, its boiling point, its boiling point is 4 degrees Kelvin. That means 4 degrees above absolute zero. We talked about absolute zero. That's when volume ceases to exist. That's when there is no more matter, right? To create even aqueous helium, under normal conditions, atmospheric pressure, it's virtually not possible. You would have to, in other words, these forces of attraction are extremely weak to the point where helium almost always stays in gaseous form. Okay? You will see that this varies, though. Obviously, the more electrons, the bigger the element is, and the more electrons it has buzzing around it, you can see where it's going to increase its amount of intermolecular force because more dipoles are going to be easier to form. Okay? You get big metals, especially, that have tons of electrons buzzing around the outside of them. It's a lot easier for this to get lopsided the more electrons there are. And as a result, the weak forces of attraction between the same types of atoms and molecules can start holding together a little bit stronger than, say, helium or hydrogen. Obviously, think about hydrogen. Hydrogen only has 1 electron. So there is no way that, it's even going to be harder to create a situation of attraction between hydrogens as opposed to even helium. Okay. So how strong are these dispersion forces? Not very. Okay. Now they will vary according to the type of molecule that you're dealing with. Some are stronger than others, but they all are very weak. They're the weakest possible force that exists in the universe between matter. Okay. It depends on how easily we can polarize these electrons. And I already talked about this. The more electrons we have around an atom in the molecules, the more we have around them and the farther away they are from the nucleus, the easier it becomes to create these intermolecular forces. The easier it is to get these instantaneous, what's called instantaneous dipoles, okay, where they just spontaneously exist and then they're gone. Okay. Now realize what I'm talking about here, okay? I want to make sure you understand the difference. When I take it that slide where I had a helium atom and another helium atom and they were positioned next to each other and the partial positive was attracted to the partial negative area, realize that is not a chemical bond. We are not, the forces that we're talking about coming together here are not the forces that make molecules. Those are chemical bonds. CO2, the bond between C and O in CO2 is an overlapping of actual electrons that creates a compound. It creates a molecule of CO2. That's not what we're talking about here. I'm talking about as a CO2 molecule is floating around and another CO2 molecule is floating around, what draws them together? It doesn't change their chemistry. It doesn't change what they are, just where they are fixated in space at any given time. Okay? There's a difference. Make sure you understand what we're talking about. Okay, so the strength of the dispersion force is going to get bigger and bigger the larger the molecule that you have. Okay, so it would make sense then, right? The stronger these intermolecular attractions are, the harder it is, the more energy it's going to take to separate them from one another, right? So let's relate that to boiling point. Because when something boils, we don't change its chemistry. All we do is change the state that it's in, right? We take it from liquid to gas, but it's still the same thing that we had. So why do certain things have different boiling points than other things? Because if I take alcohol and boil it, it's not going to take very long at all to turn alcohol into a gas. It will take more temperature, a higher temperature, to convert water into a gas. So why? And it has to do with how well alcohol molecules are attracted to one another and how easy they are to pull apart from each other as opposed to water molecules. So the stronger the attractive forces between molecules, the higher the boiling point, okay? Assuming our substance is pure. Likewise, the higher the melting point. It's going to be harder to pull them apart, so it's going to have a higher temperature for its melting point and its boiling point. So take a look here at some noble gases, helium the smallest, xenon being the largest here. And these are pure substances, and these are nonpolar, obviously. They don't even react with anything, right? If these are completely unreactive gases, then why the difference in boiling points? Well, molar mass, notice how big of a difference there is in the size. Molar mass includes protons and neutrons, right? So the bigger the molar mass, the bigger the nucleus is going to be. The bigger the nucleus, the more electrons you're going to have floating around it. So molar mass is indicative of size here. Notice how much bigger an actual xenon atom is than a helium atom, right? So because xenon is so much bigger and it has so many more electrons flying around the outside of it, they can disperse much more easily and create these instantaneous dipoles a lot easier than what helium could. As a result, look at the boiling point difference. Okay? It's a lot harder to boil xenon than it is helium. However, realize still how easy it is to boil xenon. Xenon boils at 165 K. Convert that to Celsius, that's still really, really cold. Okay? So xenon is going to exist as a gas under all natural conditions, unless you can drop it that cold. This is at normal pressure, of course. But if we can take it now and just drop the temperature to 165 degree Kelvin, then we could get liquid xenon as opposed to gaseous xenon. In the case of helium, realize absolute zero is the absolute lowest temperature we can ever even theoretically achieve. Look how close to that we have to get just to get liquid helium. Okay, so interesting stuff. When you look at now our sun, we can of course get liquid helium under intense pressure systems, intense gravity that's pulling it all in, intense pressure and all that kind of stuff. Our sun fuses this. It takes helium sort of like in a liquid form. It's more like a plasma, but it can take liquid and hydrogen and fuse them together to make things like lithium. And in the process, its nuclear fusion releases a ton of energy. We see that energy, we feel that energy as it's radiated out from the sun and comes towards us. But that's interesting too, because we don't talk about this much in this class, nuclear chemistry. But if you look at the periodic table, we've learned enough about it now to know that we can look at a hydrogen atom and see that it's theoretically, it's easy to build a helium atom from a hydrogen atom, right? What is a helium atom? It is 2 protons and 2 electrons, right? 2 protons, 2 neutrons, 2 electrons. That's a helium atom. What's a hydrogen atom? 1 proton, 1 electron. So if I could figure out a way to take a hydrogen, take another hydrogen, cram it together, and make a nucleus that now consists of the proton of each one of those, what do I have? Helium. I've got a nucleus with 2 protons. Okay? Now, as far as where the other neutrons would come from, that's a different chemistry that we're not going to talk about in here. Things degrade, things form, things like that. But then you bring in your electrons that you need and everything like that. So you could actually fuse together, and then you could take helium, you could take hydrogen. What happens if you took a helium and a hydrogen and fused it together? What could you make? 2 protons, 1 proton, cram it together to get 3 protons. What do you got? Lithium. Add another hydrogen, you get beryllium, right? You could keep going. You could build all the elements on the periodic table, and that's probably what the universe has done. All you need is hydrogen to start with, and you need massive temperature, massive energy, a massive explosion to facilitate all of this, and then over time, things combine with other things, and you can see a growth, and you can see how you could start with something like hydrogen and end up with everything else that we have on our periodic table. It's interesting that, to support that, you look in the universe, and by far, the most, hands down, not even comparable, not even worth measuring, the most abundant element in the entire universe is hydrogen. Okay, it's out there. It's floating around everywhere. There's these awesome pictures from these telescopes in space of these giant hydrogen clouds that are just floating around out there sometimes. Really cool stuff. Anyways, and that's what a star is when it first formed. It's a big burning ball of hydrogen gas. Enough hydrogen kind of just accumulates in one spot. Gravity starts to pull it all together. And as everything starts to collapse in, energy increases, temperature, friction, pressure, boom, it creates an explosion that ignites it, and then you get this explosion of hydrogen. Things start fusing together. You get heavier elements start forming so that when the star burns out, you get heavier elements, like in the core, stuff like that. You can, like a lot of the meteors and stuff like that you can find flying and that hit in, have like nickel and iron cores because of all this nuclear fusion that happened. It's really cool. And one of the things also that you can learn, I'm way off topic here, but if you take like a meteor or something, one of the things that you can look at, what's interesting, I saw a special on this a few days ago. A rock's a rock. You could have a meteor laid in your backyard and you probably wouldn't know it, right? Because what do you know? What do I know? But it's neat, though, because iron and all these minerals are a natural part of our geological processes, and they're going to be within the stone. So how are you going to know if it's a meteor or not? But you slice these things open, and you start looking at the mineral deposits that are in them. Those minerals didn't form like they did here. So you can actually see crystallized structures like little bands and like little like long, not cylinders, but like square kind of cylinder type shapes of crystallized like iron and nickel and that kind of stuff because of the way that they formed. It was liquid, it formed into a solid through a very rapid cooling process. And when you rapidly cool metal that was once a liquid, it crystallizes as opposed to just what we would find in our rocks out through here. Our rocks come from a lot of pressure and a lot of heat over a slow amount of time, and they don't form those crystallizations like you see in a lot of those rocks. So it's really cool stuff. But anyways, now here's formaldehyde, for example. We talked about in chapter 10, maybe, I don't remember, molecular geometry chapter, polarity and why it was important. Now we start seeing the importance of polarity in terms of boiling points, melting points, and how these things are going to behave. Now, permanent dipoles are what you're used to, what we talked about, a polar molecule. So when you look up and you determine the Lewis structure and you say this molecule is polar, that is not a temporarily induced dipole like we've been looking at here. That is a permanent dipole that stays and doesn't go away in that molecule. Okay? So obviously, if you have a situation where you have a bunch of molecules with permanent dipoles and they're all swimming around each other, they're going to be held together a lot more tightly than the other ones that we've been talking about, right? Now, keep in mind, though, that since these are still atoms and they still have electrons, they still also have dispersion forces, just like we talked about. They just have more than just regular dispersion forces. They have those, but they also have, on top of that, a permanent dipole. So realize that everything has dispersion forces. Some things also have permanent dipoles. So you'll have dipole to dipole attractions, like in the case of formaldehyde. You'll also see something like this in water, where the permanently positive end sort of orients itself to the permanently partially negative end. And you can see that the stronger the difference in polarity, okay? I say dipole size. I didn't go over how to measure dipole size. That's fine. Realize that's the difference in the pole of the strength, right? The bigger the lopsidedness in terms of how polar this molecule is, the more polar it is, makes a huge difference in its boiling point. So look at this. If you consider, here's what? Propane, like the kind you'd use in your grill. Just C's and H's, that's it. 3 carbons in the middle, H's all the way around it to fill up the 4 bonds for carbon all the way around. So it would be like this C with a line connected to this C, with a line connected to that C, and then an H, an H, an H, an H above, an H below, H, H, H coming off that. Okay, that would be propane. Very flammable, obviously. Look how similar. I picked these because these have similar molar masses, right? They're all about the same size. They're different chemicals. Look at the drastic difference in their boiling points. Propane boils, turns into a gas at negative 42 degrees Celsius. Now, you can get liquid propane, right? But it's under very high pressure situations. You have to mess with the pressure to force those molecules together. Under normal atmospheric conditions, as you well know, open that tank of propane, what happens? It's all gas. So under normal situations, as long as it's at least negative 42 degrees Celsius, you've got gas, because it has no dipole. In other words, it is not polar at all. There are no polar regions in this. Now, there are only dispersion forces holding things together. That's it. However, if you look at this, by virtue of the fact now that we have a CO bond, okay, and this ends up being 2 lone pairs of electrons present, that gives us the electron geometry of tetrahedral. That actually gives us a bent shape for this molecule. So our forces are pulling from different directions. You create polarity. There's a little bit of polarity with this molecule. As a result, notice there's a little bit of evidence of polarity. Not much, but a little. As a result, notice how much we've increased the boiling point just from that. Now, not a lot. It's still negative 24. It still turns into a gas very easy, but a lot more than what we were up here. Then we get into something that's even more lopsided, even more polar, as evidenced by that measurement. Notice now how much our boiling point has increased. And then we get up to something like this that is extremely polar. And we went from the same, actually a smaller molecule, a lower molar mass down here. We went from, with here, negative 42, all the way up to a positive 81.6, which is pretty good. It takes a little more juice to try to turn that into a gas. So polarity makes a huge difference in terms of intermolecular forces. So realize that. Dispersion forces. All molecules exhibit dispersion forces. Some, however, in addition to that, have dipole-to-dipole forces. In other words, polar molecules create this situation. Okay. One of the labs that we didn't end up doing, but we would have done, involves miscibility and immiscibility. I need you to know what this word means. In chemistry, we have a rule that says like dissolves like. In other words, if I want to clean fingernail polish, when I go home today, if I want to take my fingernail polish off, can I use water to do it? Of course not. What do I have to use? I can use fingernail polish remover. I can use acetone. I could even use like kerosene if I wanted to, but it would stink a lot worse, right? Why? Why doesn't water work? Because water cleans a lot of other things. It all has to do with intramolecular forces. What holds these molecules together? Okay, let me explain. First of all, let's look at this word, miscible. When you mix two liquids together, like let's say oil and water, we know very well that oil and water does not mix, right? They separate out into layers. We see this. We say then that they are immiscible. They separate into layers. They do not mix together. You can think of it as mixable, but it's technically a little bit different. So miscible and mixable and immiscible and immixable sort of mean the same thing. If something is miscible, they do not separate. They mix together very well no matter what the proportions are that you put in. You put them all in, they mix up very evenly, they're miscible. If they are immiscible, they separate out into those layers like oil and water does. Okay? So we have a rule that says polar molecules, if you want to dissolve polar molecules, whether you're like cleaning it or preparing a solution, whatever you're trying to do, and dissolve away molecules, if those molecules are polar, what you want to use is a polar solvent, a polar thing that you use to dissolve it. Okay? If those things that you are cleaning or trying to get rid of or to dissolve are nonpolar, you need to use something that's nonpolar in order to dissolve them. Okay? Why? Take a look at this picture. Here's what we know to be true, right? What is this? I can't tell. Does it say what this? Doesn't matter, but say it's pentane. Okay, so 5 carbons, right? All in a chain with hydrogens all the way around it. That's pentane. Pentane is very nonpolar, as you can imagine. Imagine 5 C's and all filled in with hydrogens around the end. Okay, equal pulling in all directions. Doesn't matter if those bonds are even polar. That's going to be a nonpolar molecule. Water, however, it's bent, right? Oxygen's here. Hydrogens are to the side, uneven. Water is very polar. It's got a partial positive and a partial negative end. So what is going to happen when I take something like pentane? That's not an oil, but it's an organic compound. I could have used any type of oil that you're familiar with. I pour that in here. Why does this form? See if you can explain it to me. Don't just read up there. See if you can explain it to me. Why does oil and water not mix? Look at it. Think about what's going on. Think about the fact that those water molecules are polar. Think about the fact that those pentane molecules are not. How does that play out to anything that's going on? What doesn't connect together? What does like each other very much? Who does more than the other? Water. Water likes itself much more than it likes pentane. Okay? So, what happens is, when you mix these two things together, there are no polar regions here. There is nothing for this pentane and this pentane to sort of orient itself, to be attracted to. There's nothing for that pentane when it positions itself next to a water to be attracted to, or vice versa. However, when you have water molecules next to each other, definitely some way to orient themselves to be attracted to each other, right? So what's going to happen is all those water molecules are going to start being attracted to each other. They're going to come together and virtually just sort of squeeze out all of these loosely floating ones that are not attracted to anything. As a result, these all come together. These get kicked out. And because they're more easily spread out, this creates a far less dense situation, right? And we know that of the two, whichever one is less dense goes to the top. Gravity pulls the more dense one down to the bottom, right? So water, in this case, actually, because it comes together, is a little more dense. They squeeze all the other stuff out, and it's sort of just like it's just sitting there on top, and you've got all these nonpolar molecules that aren't attracted to each other very well, but also definitely are not attracted to any of the water molecules. So you got to play on that. If you want to clean something, if you want to dissolve this, if this was something you were trying to clean, and these molecules, instead of being poured in here, were on a surface somewhere, like a stain, but you knew it was some sort of organic chemical that was nonpolar, okay? And you wanted to clean it, you could think about what you learned in chemistry and said, I can't clean that. That's a nonpolar chemical. Water's not going to work. That's why you go to Lowe's and you buy methyl ethyl ketone. You buy paint thinners. You buy that kind of stuff, mineral spirits, right? To clean some other stuff that you know doesn't work just because you try it. It doesn't work trying to clean it with water. Well, the reason you get that other stuff, I'm going to explain that in a second, but the way water would work is if you know it is something, normally, like the stuff that you would come in contact with every day, water is going to be just fine. It has those polar regions. It can be attracted to positive, negative areas, and it'll wipe it right up. It'll dissolve that stuff, and you can move it. However, if you want to clean something that is nonpolar, why? See if you can explain that to me then. Let's use the fingernail polish. If I use something that is nonpolar, acetone's sort of nonpolar, so we'll just say that acetone's nonpolar. Okay? Why will acetone work to dissolve fingernail polish, but water won't? I got that tingly feeling right there. I like that. You're right. And what it has to do with is you have now put two types of chemicals together that are just as equally attracted to one another, right? One is not more attracted to itself than the other, so it can evenly disperse. And yes, utilize temporary dipoles to help pull it apart. Good. All right. Now, hydrogen bonding. This is a little bit of a unique situation. I really wish they wouldn't have given it this name because it's misleading. But it is not a bond, okay? Hydrogen bonding is not a bond. It is a type of intermolecular force. When you look at something, a molecule that has one of three atoms present, if it has N, O, or F, and that N, O, or F is stuck to a hydrogen within this molecule, such as what you see here. Okay? This is methanol, methyl alcohol. C, 3 hydrogens attached. On one side of the C is an oxygen, and to that oxygen is attached a hydrogen. That could be an OH. I'm also talking about if it was a FH or if it was NH. Any of those three. Think about where N, O, and F are on the periodic table. You've used it enough now to know where it's at, right? What general region is N, O, and F? Where are they located? Just directionally, where at? Upper right, right? Upper right. What do we know about electronegativity? The farther up and the farther right we go up the table. What do I mean by electronegativity when I say that? It's how well it what? Or how much it what? Pulls what? Other what? Electrons around those elements. Okay, you're right. How much it pulls electrons towards itself, right? So when you take N, O, and F, some of the three most electronegative elements on the table, and you put them next to poor little old hydrogen, who's only one proton big and one electron, it gets ugly. Okay? Because what ends up happening is you can actually take, imagine this, NO and F can pull so hard on this electron. Now it doesn't break it, doesn't extract it and leave the hydrogen to go. It's still a covalent bond, but it's a very, very lopsided covalent bond. And it can actually take that one electron and pull it over towards the N, O, or F and leave this hydrogen proton bare and just in the wind. Okay? Now, when you have a bare and showing nucleus that is only one proton, what you have is virtually an exposed positive charge, right? Think about that. That happens, it's a unique situation because no other combination gives us a big difference like this does. Anything besides N, O, and F doesn't have enough of a pull to make this happen. Anything besides hydrogen always has other electrons there to sort of make up for the difference or whatever. But we have hydrogen now with its one sole electron, something really strong like NO and F that are pulling it over, but not enough to pull it all the way off and kick it loose. That's probably be better for hydrogen, but it's not. It's pulling it over really, really far, but still hanging around, with hydrogen still hanging around. But it shows and bears its nucleus at this point that now has a positive charge. So what you create is a dipole moment that is not like your permanent type of dipole. It's not just like a dispersion force. It's actually what's a special situation that we call hydrogen bonding, or a hydrogen-related intermolecular force. Okay? So in the case like this oxygen is really pulling this electron towards itself and giving this bare proton sort of a partial positive exposure here and a partial negative thus over here. So when another one of these comes up to it, the same thing is happening on it. So look how it can orient itself. This hydrogen is somewhat attracted to this negative region over here because of differences in electrostatic charges. Likewise, another hydrogen could be attracted to that oxygen over here, and this thing starts to hold itself together reasonably well. So what you'll find is that things that have hydrogen bonding in them, that involve N, O, and F connected to the H like that, have pretty high boiling points for compared to other molecules the same size, okay? Because they're held together a lot better. Now, this is not a chemical bond. Okay? Does water have hydrogen bonds, do you think? Does it have a situation where the oxygen is pulling on the hydrogen? Sure it does. It's O with two H's on it. O is pulling both of those H's to the point where it becomes pretty polar because you have a partial negative with the O, and you have two hydrogens exposed, nuclei exposed. Both will end up with being partial positive. So you can start seeing now why water doesn't evaporate all that well compared to a lot of other liquids, because it's held together not only by those weak dispersion forces, not only by the fact that it has a permanent dipole, it has both of those, but also because its permanent dipole is because of something extra special, because of what's called a hydrogen bond, the use of hydrogen and oxygen, or hydrogen and nitrogen, or hydrogen and fluorine to create an even stronger situation that holds these things together. So you'll find that hydrogen bonding as an intermolecular force even kicks up our melting and boiling point even farther for a lot of these things. And obviously these things are going to have a high solubility in water. They're going to want to dissolve in water very easily if it's hydrogen bonded, for obvious reasons, because there's a lot of polarity there. And that is a lot for the water to be attracted to. So, okay, now keep in mind that this is really strong. This is the strongest type of intermolecular force that we've talked about yet. The strongest is hydrogen bonding. The next strongest is these dipoles, permanent dipoles that we've been talking about. Okay, the dipole-dipole moments, like with polar molecules. That's the second strongest. The weakest, of course, is the dispersion forces that we've been discussing. Now, this typical dipole-dipole, this would come from polar molecules, right? The typical dipole-dipole compared, well, sorry, the other way around. The hydrogen bond that's present with the dipole-dipole creates about a 10 times stronger attraction than a regular polar dipole-dipole situation. So obviously it's significant, a lot more. However, realize this is not a chemical bond. This is not a chemical reaction that joins these two things together, right? Because if you look here, this force of attraction is still only about 2 to 5% of the strength of an actual covalent bond, which is what's holding this carbon and oxygen together, and this carbon and hydrogen, for example. That is a ton stronger than this little force right here, okay? So you can hopefully put it in perspective and see just how these compare in terms of strength. Biologically speaking, anybody know where we see hydrogen bonding and where it becomes very important in our body? Nobody? Bueller? DNA. It holds the sides of your DNA ladder together. When you take A and T and C and G and put them next to each other, there is no chemical bond that reacts them and glues them together. Instead, you have, like between A and T, there are two sites that come together, two polar regions on the A, two polar regions on the T that come together and form a hydrogen bond. Not a bond, an intermolecular force because of the presence of hydrogen with that nitrogen. Remember they're called nitrogenous bases, right? We've got nitrogen, we've got oxygen in there. We're going to start pulling on these hydrogens and burying them a little bit. You're going to have a pretty strong force that holds that DNA molecule together. Between the C and the G, there's actually 3 places where this little attraction happens. So it's held together even better than the A and the T. Now, why is that important? Number one, it gives DNA enough sturdiness so that it does not fall apart very well at all. It doesn't fall apart very easily. Okay? It's much stronger than the typical intermolecular forces. However, we do not want our DNA to be covalently bound together like this. That would require far too much energy for us to break it all the time like we do. We have to open it up, replicate, transcribe, translate. We could never do that unless it was just this, holding it together. It would require way too much energy to constantly be breaking actual chemical bonds. So it's good. It's a perfect balance. Very important biologically. Okay? So you can see the difference here. Notice that these are about the same molar mass, ethane and methanol. However, there's a huge difference between ethane and methanol because of this. It creates a situation of hydrogen bonding so that when neighboring methanol molecules come up there, they can orient themselves and be more attracted to each other to the point where even though you're only off by 2 grams per mole in terms of the molar mass, huge difference in terms of boiling point, huge difference in terms of melting point. Okay? Not only that, but huge difference in the solubility of it in water. Right? This is immiscible in water because it's nonpolar. This is miscible because of this hydrogen bonding and the polarity that it creates. Methanol can mix in with water. Ethanol can mix in with water. Right? That's, if you ever make drinks, you know that to be true. I'm going to wrap this up and we'll take a break here in a second. But intermolecular hydrogen bonding, same thing that we're talking about here. This just shows you a picture of it. There's HF and how they would orient themselves. Here's a water molecule, how they would position themselves relative to one another. And this is everything that we've been talking about here. So it's just a picture. Okay, I've already talked about this, the exposure of the proton. I just got ahead of myself, so I want to skip this. Already said that. These are not chemical bonds. I talked about the importance of DNA. Also, protein structure, not just DNA, but the actual proteins and how that's all held together. That's all hydrogen bonds. So you look at that, one thing I guess is people don't understand, not that it's a big deal, but when you read over those chemistry chapters in your A&P books or whatever, you read about hydrogen bonding, it's not really a bond. It's not a chemical bond that draws matter to, locks in matters and matter into new compounds or anything like that. It's just a force of attraction between molecules. That's it. Okay, and this is sort of the same thing. The creation of this is a little bit more polar, but notice the presence of this creates not just a regular polar situation, but actually hydrogen bonded situation, so it's even more. So what that means is, for example, the solubility in water. Notice how these compare. This is completely nonpolar, insoluble in water. This is polar. I can get about 7.5 grams of that in 100 grams of water. However, this is hydrogen bonded polar. I can actually get more of it, almost 9 grams of it dissolved in water. So that becomes important. Here's a good summary. Make sure you understand this. The three big forces that we've been talking about that hold things together: dispersion forces, dipole-dipole forces that come from polar molecules, and hydrogen bonding, okay, which is a result of polar molecules, but also when in a special situation when you have hydrogen bonded to F, O, or N. Okay, it's a little bit stronger. So let me ask you this before we take a break. If you have a polar molecule, does it also have dispersion forces? Yes or no? Yes. If you have dispersion forces, do you have hydrogen bonding? If something has dispersion forces, must it have hydrogen bonding as well? I heard yes, so it's all yes and no. The answer is no. You don't have to have hydrogen bonding just because you have dispersion forces. However, if you have hydrogen bonding, must there be dispersion forces present? Yes. Everything has dispersion forces. Not everything has permanent dipole-dipole forces. But everything that does have permanent dipole-dipole forces also must have dispersion forces. Make sense? Even fewer things actually have hydrogen bonding forces. If it has hydrogen bonding forces, it's going to have dipole-dipole forces. So it's also going to have dispersion forces. So we can look at this as whatever's below includes everything above it, right, on this chart. This has nothing but dispersion forces. This could have both. This would have all. Okay, that's the way that works. Okay, let's shift gears a little bit. I want to focus on solids for a minute and just the different properties of the different types of solids that we have. Notice I have types of crystalline solids. We had amorphous. We talked about amorphous and crystalline solids. It's kind of hard to categorize amorphous solids, obviously, because they're without shape. So let's look at the organization with crystalline solids, and we can see that we can actually break them down into three big categories. Okay, so kind of understand the difference here. Molecular solids versus ionic versus atomic. Just think about what that means. You know what a molecule is, right? Think of ice, for example, with molecules of water. The individual molecules are what locks together, positions themselves to create this solid. Okay. Notice that a lot of times you get just dispersion forces sometimes holding this together. But you can have, like in the case here, hydrogen bonding holding this together, right? The intermolecular forces that are there. But generally, though, it doesn't take much energy because it's still only intermolecular forces, right? That's the only thing that's holding all of this together. So, across the board, generally a pretty low melting point. It's pretty easy to melt a lot of what's called molecular solids. Ionic solids are different because what we have here is, like salt, for example, what holds solid salt together is not intermolecular forces. It is actually chemical forces, chemical bonds, ionic bonds, right? We have a cation, we have an anion. They are positioned together where one takes and one gives, and they are in an alternating arrangement, a three-dimensional structure that creates this. That is different than what's going on over here. The only thing holding this together is intermolecular forces. These are actual chemical bonds that hold this together. As a result, this is much more tightly held together, as you well know. Imagine how, heating a grain of salt and trying to melt it versus trying to melt ice. There's a big difference. These have really high melting points. It takes a lot more energy and a lot higher temperature to melt ionic solids because they are resultant from a bond, not just an intermolecular force. Atomic solids are a little bit different. They're similar to this one, I suppose, but realize that you don't have opposite charges there to attract each other. What you have are a bunch of atoms, usually a metal type of atom, that are pure, only one type of atom that are present. And they sort of are bonded together in sort of a weird way. I'm going to talk about in a second how to think of this, because we haven't really talked about that. We haven't talked about how you could have iron, a lump of iron and nothing else. What holds that lump of iron together? Well, it's pretty sturdy. Okay? It takes a lot of energy to melt it down, too. So it's likely to be more than just intermolecular forces. And it is. And I'll show you that here in a second with a picture. But depending on the type of element involved and the chemistry that's particular to the particular atoms of the whatever element we're talking about, you're going to have variable melting points with atomic solids, like pure aluminum, pure iron, that kind of stuff. That's different than what we've got going on over here. So we've got molecular solids with a low melting point. Ionic solids have a really high melting point. And then with atomic solids, it just varies. Okay, we've already talked about this. Here's an example of molecular, like dry ice, CO2. It's a whole bunch of molecules that are positioned together. Chances are what's holding them together are one of the three types of intermolecular forces. In the case of CO2, just dispersion forces. In the case of water, not only dispersion forces, not only dipole-dipole forces, but also hydrogen bonding. Okay. Pretty low melting point, also pretty low heat of fusion, because those two are related, right? One is the temperature. Melting point is the actual temperature. Heat of fusion is the measure of energy that's required to do that, like kilojoules, calories, something like that. Okay, I already mentioned this crystal lattice that we get, this three-dimensional lattice alternating ions actually forms a chemical bond, and that forms these what's called ionic crystalline solids. Very strong, a lot higher melting points, a lot higher heat of fusion than their molecular solid counterparts. Now, as far as atomic, here's like an aluminum can. Notice all you have is pure aluminum around there. The composite units that we're looking at here are just individual atoms, not molecules. Okay, not cations and anions, just one type of usually metal atom here. It's going to vary depending on the atoms involved, but I do want to show you, before I discuss how, for example, all the gold in this is held together, I want to real quick look just at, as we look at this picture here, let's go back a few. This one. Notice that we have crystalline and amorphous solids, right? So let's break down crystalline because there's branches of them. We look at crystalline, we have molecular crystalline solids, ionic crystalline solids, atomic crystalline solids. Okay? Typically, you can see why that's called a crystal and that's a crystal. It looks like what you think a crystal would be. But realize, it's not just about what you think a crystal is. What you think a crystal is just one example of a crystalline structure. Crystalline just means it's locked into a particular shape. So that could even be a crystalline structure. Okay. All right, now I want to take this category right here and divide it again. We're going to look at atomic solids by itself. That's what this next thing is, the next flow chart that you see. Let me zoom through these. Oops. Okay, so now let's look at the atomic solids, atomic crystalline solids. We have, again, three types that they could be. Okay, so keep with our subdividing here. We could have, like as in the case with silicon, if you had a bunch of silicon all around itself, notice that silicon has 4 valence electrons, right? Just like carbon does. Silicon can form 4 bonds all the way around itself. If you put silicon or carbon, either one, like in this case, you could have covalent bonds, actual bonds, that hold all these atoms to each other, okay? Such as in this picture right here. There's a diamond. Imagine if you could look at a diamond, what you would see is pure carbon atoms, nothing but carbon, all covalently bonded to itself over and over and over. And the reason it has all these sides and all these faces is, for the same reason like when we made our molecular models, and I told you you could think of a pyramid where there's 3 points, you could lay a flat side on it and that kind of stuff. That's why you get all these facets and all these different angles and stuff like that. A lot of geometry, a lot of sides that creates a lot of light reflection and makes it sparkle and stuff like that. So there's pure carbon. Here's pure silicon. They're actually covalently bonded to the point where when you look at like this silicon chip right here, this is nothing but silicon and it's all covalently bonded. This is a giant molecule. This is not microscopic anymore. You are now looking at a giant, huge molecule. When you look at a diamond on a diamond ring, that's one giant molecule of carbon atoms all bonded together. Pretty cool. Obviously, since it's actual bonds that hold that together, hugely high melting points because you would have to overcome a covalent bond to break this. It's a lot of energy necessary. You could have, though, non-bonding, like take xenon, for example. Xenon is a noble gas. We know it doesn't react with stuff. And the only thing that's going to hold a xenon atom next to another xenon atom is dispersion forces. That's it. So when you put them together, obviously it's not going to take much energy and a very low temperature to melt it. It's going to be easy to do. So they have very low melting points. Okay? But both of them are just atoms. Both of them are examples of atomic solids. You could take xenon with enough laboratory conditions and turn it into a solid, but realize it's only very loosely held together. Once it's warmed up a little bit, it's all going to disperse out again. Okay? So these are both, you get a big difference between all three of these in terms of, even though they're all atomic solids, how they actually behave because of what makes them atomic solids. Now, in the case of what's called metallic solids, like what you're used to, pure nickel, pure iron, in this case pure gold, pure silver, whatever, they are actually held together by a different means than what we've ever talked about so far. I'm just going to mention it here. I'm not going to go into too much detail with it. But they're held together by something different called metallic bonds. And because of the difference with each metal and how the electrons are structured in their electron configurations and things like that, it varies a lot in terms of how much energy it takes to spread them apart and how much it takes to melt them. So we can't explain that right now in this class, but as far as, I'm going to skip this one. This is covalent solids we've already talked about. Also, before I get into that metallic bonding, we know that diamonds is the hardest substance on Earth, right? It'll cut anything else. Think about now why that is true. Carbon is the most tightly covalently bonding atom that exists on the periodic table. Right? It's very versatile. It's 1s2, 2s2, 2p2. The 2s2 and the 2p2, I mentioned this before, but they hybridize into 4 equally energetic electrons on the outside. They form tight, cohesive bonds with everything that it bonds with. And it bonds on all sides, all 4 bonds. Okay? When it does this and you get carbon bonded to nothing but itself, imagine the strength of those bonds. It's the strongest possible scenario of bonding that exists in matter as we know it. Okay, so as a result, diamonds are the hardest substance that we can have. Now the difference, obviously, coal is not, right? But it's pure carbon as well. It also has to do with the geometry involved. This is almost perfectly distributed. Okay, all the energy is equally shared amongst all the angles and everything like that in a diamond, whereas coal obviously has a lot of other impurities. Chances are it's not going to be pure carbon, but it could be. If it is pure carbon, it's not organized in the most energy-efficient way possible, so those bonds are a little easier to break, so they're not as hard. Graphite in your pencil, obviously, is much softer, otherwise you wouldn't be able to write. Okay, but that has to do more with its structural arrangement as opposed to just the fact that it's carbon. Well, it has, yeah, partially, but it could be, no, because you're not going to ever have, like, one of the things I told you is you're never going to have a carbon atom that is not bonded completely. So, like a double bond kind of thing, or... Sure, that's one way it could happen, but more than likely, what you're going to have is differences in lengths and angles that are associated with this as well, especially because of impurities that are present. Distance between, like the space between, that kind of stuff. Okay. I mentioned xenon, only dispersion forces holding that together. Metallic bonds. Let me show you this is what I'm getting at right here. As far as what these metallic bonds are, one way to think of it is islands of cations in a sea of electrons. So imagine that. If you have a metal sample, we know that metals like to form cations, right? They like to lose their electrons. So when you get a bunch, what makes a solid metal all stick together? When you get a bunch of metal ions or metal atoms all together, they can feed off of each other. And they don't really have a place to give their electron to, so they donate it to a sea of floating electrons. And that sea then sort of swarms all throughout this cation. It's not really a mixture, right? But this a whole bunch of cations that are in this metal cations, and there's interactions between any given time having access to and wanting to lose that electron. Because you know that it doesn't possess a charge, right? We know that the only time a metal is going to have a charge is when it gives up its electron. And then when it accepts it back, it's going to be charge neutral. And we know that when we have a lump of iron, it's charge neutral, collectively. That doesn't mean every single atom in it at that instant is charge neutral. What it means is that everything is sort of balanced out. Okay? So within a piece of metal, what you have is the constant, because of everything surrounding all these cations, the constant losing and gaining of electrons all simultaneously happening all over this. It's kind of hard to explain, so that's why I'm not going into it. But just realize that's a different type of bonding than what we've talked about that holds all these metal atoms together. Which explains a lot in terms of why they are so conductive, right? Conduction is the movement of electrons through something. So when you have this created sea of electrons, it becomes very easy to imagine that if I could put a charge right here and deliver electricity to this, it's going to conduct electricity very well because there's already a sea of electrons for it to travel through. It's very easy to get them to move directionally from one place to another because there's already that situation that exists in metals. Now I'm going to end on this. Water is very unique. I want to throw this in at the end. There's something very, very special about it that is we take for granted all the time. It's an odd case in the world of chemistry. It's absolutely essential to life. We use water for more than just to quench our thirst, right? It dissolves everything that we need to dissolve in our body and takes it where it needs to go. On our electron transport chain during cellular respiration, it absorbs all the oxygen absorbs all the free electrons and then forms water in the process. We use water to constantly break chemical bonds, like through digestion and all kinds of stuff in our body. We insert it, we use it to split things apart. What we use water for is you can't express that value enough. To the point where we are so dependent on it, if we understand life elsewhere to be like life is here, it would have to have water. There's no way that life's processes could exist without it. So that's why a lot of times when they're looking for life, one of the things that's a big deal is whether or not there is water found in this place where they think life might exist, such as some of the moons that are in our solar system, or elsewhere, planets that they talk about discovering, things like that. Is there water there? Does it look like at one point there was water there? That is suggestive of the possibility of harboring life. But what's really cool about water, if you think about this, you probably haven't thought about it before, but you'll notice it now. It is the only chemical that exists under natural conditions in all three states of matter. Solid, liquid, and gas. It exists on our planet. Water vapor, ice, and water. Right? Now, of course, our planet is over 75% water. Right? Our whole entire planet. Of that 75% of water, 99% of it, well, let me rephrase. Of that 75%, 1% of that 75% is all we use of our fresh water. So where is the remainder of all that? I mean, obviously, of the fresh water that exists, we only use a very, very small amount of it. So where is the rest of the fresh water? I don't think we really realize how much is in the ice caps, how much is in those polar regions that seem to be melting away, and all this kind of stuff with global warming and everything that's happening. We only use such a small portion, and yet you think about how much water I know I go through and we go through on a daily basis, how much the humans in general must use, and how little that is representative of the total that's actually there. The ocean is just huge in terms of what's there. But it is very unique, and it's very interesting that that's the only chemical where that is true. And I'll tell you what else is really neat. Well, obviously this is true. This is what was not what I'm talking about, but it is obviously the most common solvent, the most common thing we use to dissolve stuff in. But what's really cool about water is it is also unique and different in the fact that, well, let me ask you this. If I wanted to take liquid iron and I wanted to freeze it, and I wanted it, in so doing, and I lower the energy and I draw the molecules closer together, what happens to the density of that iron? Does it increase or decrease as it's coming together? It's increasing, right? To the point where now if I have solid iron and I have a big tub full of liquid iron and I take my solid iron and I drop it in liquid iron, what will happen? It'll sink. Water, in the case of water, that's not true. What happens with water is, as water gets colder and colder and colder, and as it comes together and it starts to get closer and closer because the energy is being removed, molecules can slow down in their molecular movement, it gets colder. For a while, like everything else, it becomes more dense the colder it gets. However, the most dense that water will ever get is 4 degrees Celsius. Okay? At 4 degrees Celsius, under normal pressure, the water is as close as it's ever going to get, because what happens at 4 degrees Celsius is the water does this. It comes in, it gets colder and colder and colder and colder, and then bam, 6 degrees Celsius, 5 degrees Celsius, 4 degrees Celsius, 3 degrees Celsius, 2 degrees Celsius, 1 degree Celsius, freezing. It expands. After it gets below 4 degrees Celsius, it reverses. It's coming together, getting more dense. All of a sudden, it becomes less dense. It's like that one toy that, I think it's the same toy, and they bring it back every year because they never actually sell it. At Walmart, when you're checking out, those little toys at the end, when you're, after you walk past the register, there's always this one thing. It's like this ball, and it's like it stretches, right? It opens up, and then you can collapse it back down, back and forth. That's sort of what happens with water. You go in. Starts out this big, it's getting colder, 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 and then all of a sudden it starts stretching back out again, and then it stops. Okay? Why is this important? This is of immense importance in the biological world, because it creates a unique situation where the solid form of that substance is less dense than its liquid form. So what happens to ice? It floats. It doesn't sink. Think of what would happen when that cold water at the surface starts to form ice. If ice was more dense than water, what would happen? It would all sink down. The ice would fall to the bottom, trap everything underneath it. It would kill all the vegetation. The fish would never be able to live. Nothing would be able to exist. Okay, our freshwater ecosystems would get turned upside down, literally, okay, in a bad way. It is very important that ice forms at the top and still leaves all that space underneath it for things to thrive and for things to live. Ice forms from the top down in a pond. It doesn't form from the bottom up. Okay, very interesting. That doesn't happen elsewhere, just with water. Now it is interesting though that our ponds and our smaller freshwater ecosystems do experience turnover. A couple times a year because of temperature differences. When water starts to cool, it becomes more dense. I'm not talking about freezing, but just as the temperature drops in general. And that heavier pockets of water start to sink within those other pockets of water. Whenever the surface temperature becomes cooler than the temperature below it, that surface water starts to sink, and it displaces and pushes up the water that was on the bottom. And it flips all that water over, and it recycles all those nutrients and keeps our ponds healthy in terms of the ecosystem. Keeps everything distributed, flips things over. So it's actually very important. Think of how the world would be different if solid ice was more dense than liquid ice. All right. One other thing to point out here is water is very small. It's only 18 grams per mole. Very small in terms of its molar mass. If you look at anything else that has a molar mass that small, you will find that it is a gas. Water is not. It's a unique balance of polarity, hydrogen bonding, that allow it to, unlike anything else its size, remain a liquid at room temperature as opposed to a gas. Very unique. So it gives it a high boiling point compared to everything else its size as well. Also important. Expands as it freezes. I've already talked about that. So, all right, that's it. Test when we come back.